All right, guys, this is lesson 7 of topic 1. This is our last new lesson of the topic 1, and so you will be having a review tomorrow and the test the next day. Now, for this activity or this block, you're going to need several supplies. You're going to need 10 sheets of patty paper. You're going to need your compass or something to use as a straight edge. And attached in your Google Classroom for this block, you have a paper entitled Triangles You Need for this lesson. So you need these triangles. You'll also need your notes, of course, to refer to too. And so what you're going to do at the beginning of this lesson is to take these 10 sheets of patty paper and you're going to trace each one of these triangles twice. And so you're going to trace the equilateral triangle on 2 separate sheets of patty paper. And when you are doing so, you're going to use your straight edge to make those nice and crisp edges and label each one. So when I trace the equilateral triangle, I'm going to label that sheet of paper equilateral. And then I'm going to do that a second time. And then I'm going to do the isosceles twice. Label, trace, label, trace, label. Okay, so I'm going to go ahead and pause this, and you also pause it and get those traced. Okay, so you should have 2 acute scalene, 2 right scalene, 2 obtuse scalene, 2 isosceles, and 2 equilateral triangles that are all traced and ready to go. So you will not need this sheet any longer. You'll be looking at your notes as we're talking about a few things. So today we're going to be making and justifying some conjectures about incenters and circumcenters. But before we do so, we're going to do a little bit of a review of what we've learned so far in topic 1. So remember, we've been using inductive reasoning. And inductive reasoning is when you are making your judgments or conclusions based on patterns. And you do this every day. You just didn't probably know it was called inductive reasoning. We learned how to make conjectures, which remember are statements that we believe to be true based on our observations, but they have not been proven to be true. Once we prove them to be true, they will become theorems. So noticing patterns is a really important concept that we use in math a lot, and especially in the building blocks of geometry. Now, we focused on angle bisectors for 2 different lessons, and we made 2 claims about angle bisectors. One is, don't forget, this is the angle bisector, ray AX, and we can tell that by these arcs in the parts that it created, showing that those parts are congruent. Remember, we put points on the angle bisector, and we made those perpendicular distances to each one of the sides, and found that those distances were congruent. So every point on an angle bisector was the same distance, and we have a word for that, equidistant, from both sides of the angle. So B was the same distance from this side as it was from this side. C was the same distance. D was the same distance. We also learned that if we make the 3 angle bisectors of a triangle, that they all intersect at a single point, and that point was called the incenter. Remember that the incenter was the center of the inscribed triangle that touched all 3 sides of that triangle. We then looked at perpendicular bisectors, and we learned a couple of things about them as well. So remember, we learned if a point is on a perpendicular bisector, then it is the same distance, or equidistant, from each of the segments endpoints. So I was the same distance from R as it was from K. A was the same distance from K as it was from R, and so on. Then we learned if we make the 3 perpendicular bisectors of a triangle, we can tell that by the right angle symbols and the congruent symbols here. They intersect at a single point as well, and that point is called the circumcenter. The circumcenter is the center of the circle that circumscribes the triangle, or the circumscribed circle, sorry. Now let's review a couple of questions from assignment 1.5, because this kind of makes a conclusion of what all we learned from angle bisectors and perpendicular bisectors. So it says you have learned that the intersection of the angle bisectors is called the incenter. This special point is shown here. This is point I. Which of the following statements are true about the triangle's incenter? And it's a select all, so there's probably more than one answer. So the first one says it is equidistant from the three sides of a triangle, and that is true. I to O, I to N, and I to M are all radii of the inscribed circle, and a radius is constant through the same circle, so those are all congruent lengths. So that is correct. The incenter is equidistant from the three sides of the triangle. The second one says it is the point at which the triangle's angle bisectors intersect, and that's correct. Remember, all these dotted lines were angle bisectors. We can tell that by the arcs in the parts of the angle that they separated it into. And so that is correct. Angle bisectors intersect at the incenter. C, or the third one, says it is the center of the circle inscribed in a triangle. And that's correct. The circle inside a triangle is called its inscribed circle. And so that is also correct. And the last one says it is equidistant from the three vertices of the triangle. So it's saying I is the same distance to J as it is to L and to K. And that is simply not true. You can obviously see just by looking that I is closer to L than it is to J. And so we would not select that as a choice. It is not the incenter that's equidistant to the vertices. It's the circumcenter that is. So that brings us to the next question. A triangle circumscribed circle is a circle that passes through all three vertices. So if we had a circle that went through N, P, and K, that would be the circumscribed circle. What must be true about triangle PKN's circumscribed circle? And again, this is a select all. The first one says the incenter is the center of the circumscribed circle. No, incenter does not go with circumscribed. Incenter goes with inscribed. Circumcenter goes with circumscribed. So that is incorrect. The second one says that segments CK, CN, and CP are all radii of the circumscribed circle. And that is correct. If we had a circle that went through these vertices, then C to P, C to N, and C to K would all be radii of that circle. That is correct. The circumcenter is the center of the circumscribed circle. Yes, circumcenter goes with circumscribed. That is correct. And so obviously the last one, none of these statements are true, would not be correct. So our question today is, will the incenter and the circumcenter of any triangle be interior or inside of the triangle? So you're going to use your 10 sheets of patty paper that you've already traced each of those triangles twice with. Okay, make sure that you labeled what type of triangle it was. So if you didn't, you need to do that before you start this. So we go from number 1 to number 3. Number 3, which is really number 2, you're going to paper fold the incenter and the circumcenter for each triangle. So in other words, you're going to have one equilateral triangle that you fold the incenter for, and the other equilateral triangle you're going to fold the circumcenter for. And you're going to do that for each one. So you have 2 acute scalenes. On one of them, you're going to fold the incenter, and on the other one, you're going to fold the circumcenter. Okay? So remember, to do the incenter, you're folding side to side, and that crease should go right through the middle of that vertex. To do circumcenter, you're going vertex to vertex, point to point, and you'll make that perpendicular bisector that will not necessarily go through your vertices. Okay, and so you're going to do that for each one. Right scalene, incenter, circumcenter. Obtuse scalene, incenter, circumcenter. So go ahead and take time to do your folds, and then go ahead and try to answer the questions on your notes. And then we'll come back and we'll check that in the next video. So go ahead and do your folds and answer these questions on your notes. The next video, we'll check those with you.